Ladies and gentlemen, welcome to our STARS tutorial on smart sensors and communication technologies for the railway applications, My name is Fritz Hübner from Berlin, Partner for Business and Technology. We are one of the project partner of the STARS project, and I guess that we will have some interesting and fruitful contribution from the Fraunhofer Institute for Reliability and Microintegration. So, to give you some words about the STARS project, at first I have to tell you that the European Week of Advanced Technologies for Railway Applications is still running, and our tutorial is a part of it. And we will have another tutorial tomorrow, and I will come in the end of this tutorial to announce you that tutorial. Yeah, one element of the this European Week of Advanced Technologies for Railway Applications is also the STARS Hack and Match Events meeting platform. Many of you already made the opportunity to create a short profile on this platform in order to get in contact with other participants of the platform. We have created some dedicated time slots where you are able to select your availability and suitable dates for meetings. In general, because it is a long-lasting platform, this platform meetings will be possible all over the time, at minimum until the 30th of September, the end of the STARS project. After that, we have to discuss to prolong this platform some months. Yeah, the STARS project is on supporting European small, medium-sized enterprises of the rail supply industry in successfully adopting advanced technologies to boost products, services, manufacturing processes, and organization. And inside the STARS project are 10 cluster organizations, 5 technology centers, amongst them Fraunhofer Institutes in Berlin, 1 digital innovation hub, 1 blockchain provider, and not officially partner, but many supporting organizations from total 14 European countries. I will put the link to the STARS project website later into the chat, and the chat you can also use for your questions. So we have one big presentation on smart sensors and smart communication technologies for railway applications, and we have 2 presenters. May I introduce Carsten Brockmann, he is group leader, and Paul Perwitz, he is part of the scientific staff, both at Fraunhofer Institute for Reliability and Microintegration IZM. I lose an M in the last, but this Fraunhofer Institute is one of the 4 institutes which are sitting in Berlin and part of the STARS project. And I give the floor to you both.
Yeah, thank you very much, Mr. Hübner, for this nice introduction, and also from our side, from my colleague Paul Perwitz and me, a warm welcome to all of you. Thank you for taking the time for this tutorial, and we are proud to share our research work and our development work of the ongoing projects. And therefore, I will share my screen, hopefully that you can see the slides in full screen mode. Is it working?
It works.
Okay, perfect. So we will like to present you today smart sensors and communication technologies for railway application. And only for you a few seconds on how we are and where we're located. Mr. Hübner already said we are located in Berlin and are part of the Fraunhofer Group Microelectronics, and we are standing for the system integration for the application part. The Fraunhofer IZM has 430 employees, including students and trainees. We have around 5,370 square meters of laboratory space and long-term contracts with several universities here of Berlin, in Dresden, and also newly in Brandenburg. Senftenberg. So this is what we are personally caring about. So our institute is starting at post-wafer level processing up to wafer level packaging, panel level packaging, and we are part of the department which cares about product integration. So we are bridging the gap between the technology and the application and the system design. Therefore, I would like to motivate on what we are understanding out of smart sensors. So let me introduce what our view is on smart sensors and smart communication systems, as we see it as an enabler for new technologies, offering new sensing opportunities, such as radar sensors, so such complex sensors, also electromagnetic sensors and other working principles. My colleague Paul will talk about this later on. And of course, we are thinking that data acquisition and analytics at the edge are also building smart sensors, meaning that there's not always a need for data communication to a centralized infrastructure, but we can acquisition and analyze the data at the sensor itself, which means that we have processing power and intelligence at the sensor edge. And at least we also need a wireless communication, or can establish, therefore build ad hoc networks for dynamic configurations, for example, for rolling stocks, meaning that from the locomotive at the beginning to the last wagon, there's the possibility to establish local networks along the train for data exchange, but also for aggregating sensor measurements, sensor data, at least for a better analysis and a view of a complex measurement problem. And for the property of being autarkic means that we also have the need for an autarkic power supply. This enables retrofitting. So if there's not an infrastructure yet, we can place sensors along the train, inside the train and outside, but also at the infrastructure. When we enable the sensors being supplied by a long-term battery, or even by harvesting principles, let's say vibration harvesters or solar cells, or even a hybrid approach of that. This is a need also for smart sensors, and implies that they have to be very efficient because of long-term maintenance cycle and long-term or long life operation. And of course, also energy saving becomes more and more dominant due to the awareness of the carbon footprint. The pictures here on the left-hand side should visualize how the IoT market, where the smart sensors are belonging to, is growing since 2016. I have the figures of volume of devices, numbers of devices, and we see that here at the right figure, at estimated 2025, we have nearly 80 billion devices connected to the IoT infrastructure. So this is a growing market, and this shows that the approach of decentralized connected devices within a network is a very, very active driven approach for different scenarios and applications. And what this could be, we see on the next slide. So the advantages of those smart sensors and of those connected sensors are that they do not need a costly infrastructure. They can build up their own infrastructure due to the wireless communication. They have more degrees of freedom. Where can they being placed? So we will later see that, for example, magnetic holders are a good possibility to put devices on places where measurement is needed, but there's no possibility to mechanically adjust the component or infrastructure due to normative restrictions or so on. So magnets could be a crucial role at this. And also rough environments are application environments which can be addressed by these smart sensors. For example, mining industry, where I have a huge area to be observed or monitored with mobile equipment. There, the wireless and smart sensors could be attached to vehicles or machineries and could measure decentralized the processes and conditions. Also, for the big topic climate change, we need more sensor data of different expertises like weather data, but also water levels and humidity of soil, and for agriculture reasons, this could also be done by these smart sensors and connected sensors to measure a huge area and to cover a huge area of measurement points. So at least smart sensors smart sensor technology seems to be invented for railway application, which have similar properties, mobile, rough environment, and a huge demand on reliability, on reliable solutions. This could be addressed by those smart sensors. And in detail means that we can detect, for example, wearing. Here on the right-hand side, this picture shows a gearbox which is equipped with a sensor, with a smart sensor here, suffered by inductive energy, supplied by inductive energy, and sending the data with a wireless communication link to a gateway here, and monitoring the wearing of the bearing, but also monitoring of and detection of cracks, overheating, and also event monitoring, vibration monitoring is possible with this mobile smart sensors. So we're coming closer to the train and the railway itself. We have tried to visualize this picture on where we can think about smart sensors here at the locomotive, but also on the wagons, keeping in mind that these sensors could be connected to each other via a local network, only with a few milliwatts of energy drawing from the battery or supplied by an energy harvester. And how this could be possible, I will show in the next slides, and give you also some application examples. We see here basic physical sensors which are commercially available for different parameters like air pressure, temperature, humidity, and so on. But we will especially focus also on radar sensors, where we get a deeper dive with my colleague. Okay, coming to the architecture of those smart sensors, how are they built and what kind of functionality do they provide? We have here the main building blocks of this smart sensors. First of all, we need a control and data processing unit, like a microcontroller, but even also DSP or FPGAs in a hybrid architecture are common in use. About power supply, I spoke already a lot. We can imagine on long-term battery supply, meaning that we reach a lifetime of 10 years or higher with a very low power approach, where we have a good power management, which is also part of these smart sensors and has to be part of these smart sensors. But also there are several approaches on energy harvesting solutions like solar cells, vibration. Also, we can here divide between inductive vibration harvesters, which have a little bit more output power on high shock events, and also on capacitive vibration harvesting due to based on a piezoelectric principle, which is more supplying energy by a constant vibration profile. But this has to be in resonance to the most likely frequency, so it's a bit tricky to adjust this kind of harvesting. And of course, we have thermoelectrical harvesters as a further option. Power management is crucial because we have to save energy. Nevertheless, we are drawing it from the battery or from the energy harvester. This means that we have to control the devices and the peripherals. We have to control communication cycle and measurement cycle. And what we are actually researching on is adaptive control. So based on quality of service levels and parameters, we are trying to adapt the system in real time in operation to save energy when the system is not actively needed for measuring or communication. Connectivity is one of the most powerful modules or building blocks inside a smart sensor, which uses the most amount of energy. But there are some optimization options, and of course, the choice of the wireless IoT protocol is crucial to the overall power demand. And what kind of protocols are available, I will show later on, and how to decide for the right protocol. I give you some advices on further slides. Sensors and interfaces, of course, for digital and analog sensors are also necessary as a building block for this kind of smart sensor platforms, and memory for data recording if communication is not possible, or also for configuration purposes. So if we consider this kind of building blocks into a more concrete architecture, we see, as I said, the low power microcontroller as the central function block. Beside this, we have peripheral sensors adapted. We have power supply and power management, but also we see on the right-hand side the outcome of two research projects that we can achieve a lot of energy saving with multiplexers and switches and level shifters, so that we can adapt to the peripherals on the right voltage level, and also switch off peripheral components which have no internal intelligence to be put in standby mode, for example. And with level shifters, we can adapt to different interfaces which are more energy efficient or energy saving. And with this, we establish some kind of a platform, or we can establish some kind of a multi-sensor platform, meaning that we are concentrating on interfaces, not directly knowing at the beginning of what kind of sensors we are connecting to the system and we are addressing, but due to a very high configuration possibilities and flexibility of the interfaces, we can change a lot of the system at the operation time, so it could be adapted to different requirements. And together, we think that this could be a very good solution for railway applications, because we have a high variety of measurement tasks, we have a high variety of different components, and also requirements, environmental requirements, application requirements. If we look at the train itself, or if we look at the infrastructure around the train, this could not be done by one system. There have to be adaptation possibilities, and this could be best with some kind of a multi-sensor configurable approach. Here, this picture show one example. We tried to shrink the size of those sensor platforms. Here we see a folded, rigid folded semi-flex substrate, which is folded to a square, not a square, a cubicle, and only with 8 cubic centimeters volume, and being attached by different modules reaching from power supply, from solar cells and piezo harvesters, up to different communication interfaces like wireless communication on the 2.4 gigahertz band, but also Ethernet for higher bandwidth and higher data rates. So this is how it could look like. Architecture based here on Bluetooth communication version 5. We have different protocols which can be adjusted on the operation time, and we have different sensors which can be adapted to that module, also being mounted on the board itself, so that the system can be adjusted via software to best fitting the measurement task and the environmental and application requirements. It's nearly €1 in size, and the weight is 4.9 grams. Here we see also some kind of infrastructure. So as I said, Bluetooth is the wireless communication link and could be directly fed into industrial PCs or via USB. So the housing is equipped with magnets. As I said, this gives the possibility to attach the device on different structures and different components on the train, but also on the infrastructure, with no need to mechanically adjust bore holes and so on, only being attached directly to the components and being able to measure vibrations, temperature, and other parameters. Here we see an application example where this kind of devices were used in a field test. So this field test was carried out at a wheel set. We see here the energy harvesting component, meaning that we used here an inductive harvester. The wheel has some discontinuities, some holes, and here inside is a magnet, and due to the change of the flux, of the magnetic flux, we have some induction voltage and current here inside this coil, and we were able to feed the sensor system with this small amount of energy, being able to measure especially vibration profile. And we see here on the right hand side at this figure, and this vibration profile was used to estimate on how stressed are the components, when is maintenance needed, and are there some events occurred during operation time, which are crucial where a special maintenance has to be carried out. At least the data, of course, could be processed at the edge, as I said, as part of a smart sensor. But of course, maintenance personnel and also, for example, manufacturers and other groups of interest are interested in the data itself. And the data could be, for example, recorded via a mobile device like a smartphone or a tablet. With a small application here, able to export ASCII and hex values and also provide graphical plots, so measurement values are directly seen here on the screen. So thank you. This was the introduction of smart sensors, and I will hand over to my colleague Paul for special radar sensors.
Hello. I'm working at the IZM in the radar group, and I want to introduce you for the possibilities to using radar sensors for radar applications. So the most of you are familiar with radar, I think so, but for those who are not, radar is meaning radio detection and ranging, and we are using electromagnetic waves to examine the relative velocity, the distance, or even the direction of objects in our field of interest. We have various kind of radar. First one is a continuous wave radar, and here we can just determine the velocity. We are using mostly the FMCW radar because we can determine the distance and the velocity of objects in our field of interest. And the third option is a pulsed radar. It's also able to determine the velocity and the distance, but for the pulsed radar we are using specific components, and this means we are not able to integrate it in small sensor networks. So the radar, since we have new developments which are leading to smaller components. This means we can use higher frequency, which means smaller wavelengths. So our antennas are getting smaller. This means we can use it for small hand sensors. You see it in the pictures right here. And since then, our radar applications are steadily growing. They are used for automotive and also for home automatization. And yes, and here are our applications. The bigger ones are using for ground penetration radar, but we are focusing on the middle frequency range, like 10 to 100 gigahertz, and we are using them here for autonomous driving, also for railway position, and for presence sensors, like in the home automatization. What's also interesting for the for railways applications is a SRR radar. Here we can measure the topology of like the track bed or a tunnel or something like this, which is also very interesting for predictive maintaining. If it comes to development of a radar, we have a lot of challenges. We have the radar range expectation, and also there we have a lot of regulation. We need the components, we have to design our whole RF path, and also the data acquisition. And what's specific complicated is the component availability, since we have some restriction in terms of dual use and so on. So what we are doing now is to don't develop a whole radar system. You can see here what's a typical development process of a radar system. There are a lot of steps, a lot of work packages, and if we are going from step 0 to the whole product, this is a very complex design process. What we are doing is we are using a toolbox. That means we we are using subgroups of our radar systems. So in terms of the package, signal processing, it means like libraries and so on. Also methods for simulations, for solving the radar equitation, for calibrations and so on. And also the electronics. So in terms of power source, power distribution network, data acquisition ICs, and so on. So we are pooling all of our knowledge we had and build like kind of modules, and we can stack these modules like like building bricks together. So if the customer comes to us and say, I want to detect like people in the room, then we are knowing what kind of radar you need, or even if the customer say, I want this specific radar, then we can, using this building bricks, like the power source and so on, and build a customized radar system which is more specific like, than commercial available eval boards, but not with a complete effort of building a complete new system. What we have done in the last years, since 2019, we are starting with this toolbox, and we used it for several applications like retail data acquisition, spatial detection, tracking of objects, also for autonomous driving or detecting of drones. We are using here these building blocks. You can see some similarities in these modules, but also some difference. So like the both radar modules in the middle, you can see the same electronical components. We just changed the packaging or the antennas. But this, we don't have the complete evaluation process. What we have done in the railways application, we had with a partner in Dresden and also with the TU Berlin, a SIM project which is called Railways, and we had to develop a sensor platform for railway traffic. This consisting out of a basis board where all the data acquisition and processing was done, and two different radar modules. We have a 60 gigahertz and a 24 gigahertz, and they were used for detecting the loading condition of a cargo train, and also for detecting the position of a speed train. So for the cargo train, we had requirements of a very high resolution. It was used to detect the condition of our axis of this train. So we measured the distance between the cargo wagon and the tracks, which was really hard to get the energy supply. It was planned to get 10 years of self-sufficient data acquisition. We had a partner in Dresden, ECD, and they built a housing with a big batteries inside. So to detect a cargo wagon, we don't need to measure always. We just measured once per hour, and at the end of the day, there was whenever you want, there was a worker, and he's reading it out with Bluetooth. The other concept was to detect the position of the train. We are using balises, so-called balises. It's like a barcode. We are driving over with a train over these balises. They are on the trackpad, and reading out the profile of these balises with our 60 gigahertz radar. The big advantages here was we can detect the position of the train very exactly, because these balises are very low cost. So you can build it on the 3D printer and put it on each of these trackpads. So it's easy to place. We don't have a crosstalk to neighboring tracks, and it's independent from like GPS or GSM. So you can always exactly say where the train is. So I just summarize. we have built several radar sensors. We have a radar kit. So we have building bricks to use the knowledge of our whole projects to build customized radar systems. We are using them also for railways, but also for different kind of projects. We are using them for gesture recognition. We're using them for presence detection in the room. Therefore, we have several frequency we are using, and also several interfaces to connect it to the data acquisition and processing. And yeah, that's it to the radar.
Okay, thank you, Paul. And thank you also for mentioning these main building blocks, such as energy supply. As you said, it was done by batteries for a lifetime of 10 years. And you mentioned also Bluetooth communication for, let's say, data exchange to a worker or a maintenance team. And at least, of course, we see here the smart sensor, so using a lot of computing power on the radar module itself. Of course, so we have here all the presented building blocks, and now I will come to the low power communication, which is also crucial in terms of energy demand, and also as we heard, a requirement for the most of the systems due to data exchange and knowledge about the status of the sensors and the systems. And therefore, in my introduction, I said that we are talking about a sensor network which is established ad hoc by a wireless infrastructure. So we can say that there's a paradigm shift from centralized to decentralized low power architectures. Only local information is mostly processed and communicated. So this has the advantage only sometimes to reach the back-end infrastructure and to save energy, therefore. We can scale those systems much better than other systems which are which have a process on let's say authorization and allocation of network resources. It could be done in the near field and, for example, along the train or along a part of an infrastructure. Reliability and robustness is an integrated part of distributed networks, because if one component fails, another one in the near field could take over. Communication passes, as here on the right-hand side, could be arranged over another sensor node if one communication partner fails. So that there's a much more degree of freedom to arrange communication than in a star topology where I have a single point of failure. Security and privacy is similar being implemented as in other star topology or backbone-based communication infrastructure systems. But as I said, in terms of reliability and in terms of security and privacy, I have the advantage that information is also distributed and not at one point located. So latency and agility is comparable to those topologies in star. It's a little bit tricky to arrange the same latency if I have a mesh network. So there are also some disadvantages. But if I compare local clusters of network partners, I can arrange lower latency than communication to a big infrastructure, where I get the latency mostly in terms of changing the different or hopping on the different communication partners. Flexibility is a big topic. I can arrange nearly freely those sensor nodes and sensor devices. They can establish always a new connection to other communication partners in the near field, and therefore it's a high agility and flexibility. Efficiency, I think I motivated just right before. Low power is a crucial parameter to those systems, but it also goes hand in hand with lower bandwidth. Of course, those systems have lower bandwidths than, for example, a mobile connection. Cost and maintainability means that we have, due to the distributed sensors, easy fixes, because some units can be overtake the functions of nearby partners without losing resolution and without losing communication path. But of course, it could be expensive if I scale those systems to a very high amount of sensor nodes. So this is a topic which has to be engineered before the solution is rolled out. The main parameter is how the sensors are communicating with each other. There's a lot of communication protocols on the market. They are sometimes standardized, but also we have good experience with proprietary approaches. I tried to give you an overview of what mainly known communication protocols and network standards are available in different bands, so reaching from the sub-gigahertz band 169 over 433 and 868 to 2.4 gigahertz. This band is nearly available, internationally available in each country. Here at the 868 megahertz, we have to have a closer look to country regulations. In the Northern America, I think it's 915, but all these protocols are mostly defined on two bands, and we see here the energy consumption of those communication protocols against the maximum communication distance. So we tried to analyze how far I can communicate with which kind or which amount of energy. And of course, we see mobile communication, GSM, LTE, NB-IoT has nearly the maximum communication range. If I have a good coverage, it's nearly unlimited because the handover and handshaking between the different base stations is done automatically. But of course, these powerful protocols have also a high power demand. Also the NB-IoT, which is more efficient than normal LTE, but on most times the high bandwidth is not needed, and therefore we can have a look at more lightweight protocols such as LoRa and Sigfox, for example, which also can generate communication distances up to 30 kilometers, but with very lower power demand. And the 2.4 gigahertz, especially Bluetooth protocol and ARN Plus protocol, draining only a low amount of energy from battery or the power supply, but they only can reach communication distances up to, let's say, 250 to 300 meters. So we have to also have a look at the maximum data rate, also compared to the power demand. And we see that Sigfox, for example, is only able to transfer 100 bits per second, where Bluetooth at the other end is able to generate data rates up to 2 megabits. And compared to the total amount of energy, this is also a very efficient way of communicating data and establishing networks. So from our point of view, from our experience, we should have a closer look at these both technologies because we used it successfully in some application examples, and I will show you on the next slides. So LoRa is a technology driven by Semtech, which offers the hardware, the transceiver for this technology, and the LoRa and LoRaWAN protocol are available for implementation. And this is a very energy efficient protocol which enables LoRaWAN enables star topology. So with a line of sight communication distance of, let's say, 25-30 kilometers, I can reach a base station. But we have done research work. It's also possible to set up mesh networks based only on LoRa, on the communication technology itself. And it's highly configurable with a so-called spreading factor. Energy demand, time on air, and robustness and reliability can be adjusted on operating time. So meaning that I can find an optimum for transmitting and saving energy. And this is a very interesting feature of this protocol and setup. Bluetooth seems to evolve to a standard in industrial sensor networks. So because it's also very robust in terms of the communication link due to the modulation technology, it has the advantage it is specified on the 2.4 gigahertz band and therefore internationally available. There are a lot of profiles which could be used in those Bluetooth stack, and it's very energy efficient. So we have implementations where we need only a few milliwatts for communicating data between two communication partners. And as you see here on the right, different topologies are supported. So the star topology, for example, from different sensors to a gateway, but also mesh networks and broadcast. This is very interesting in terms of synchronization of a network. So if you need a highly synchronized sensor network where every sensor measures at the exact same time, so this could be an approach to drive this over Bluetooth. At least the system designer has to be think about, of course, the best fitting communication technology, because this is the crucial parameter. As I said, communication draws the most amount of energy from the source, and therefore the question is how big is the number of sensor nodes needing for the measurement task. Do I need a dynamic spanning topology, and how is this topology? What requirements I have for bandwidth and communication distance, and with the presented overview, one can change out of this one best fitting protocol. And then finally, one is able to choose best architecture and topology, compare here star, chain, and mesh networks, and then design the appropriate power supply for this. I already mentioned battery as a possibility, but also supplying by energy harvesting or hybrid architectures. At least I would like to show you an example nearby the train also, but also for energy supply. So we see here overhead, high voltage overhead power line, where we developed in the recent years one sensor which is completely self-sufficient, could be mounted here on this power line on the conductor. Oops. And measuring some mechanical and electrical parameters such as voltage, current, inclination and temperature of the conductor, and therefore one is able to at least determine the ampacity of the line, but also monitoring it for hazard control such as ice loading or short circuit current detection. Yeah, with this slide, I would like to summarize. So railway technologies and application offer a lot of opportunities for decentralized smart sensor networks. We have heard about innovative radar sensors and also smart multi-sensor platforms, which include a lot of sensors and therefore measuring parameters, communication technology for establishing networks and also for communicating data to maintenance personnel and other interested groups with their advantages and disadvantages compared to power demand, communication distance, and so on were presented. And also system architectures and design processes were discussed. And we saw some concrete applications where we tried to bring in this expertise in some first prototypes tried out in a real test environment in the railway application sector. So from our side, or from our point of view, decentralized energy autarkic systems form the future of smart measurements and monitoring, and with the ability to logically analyze data locally and energy efficient, one is able to cover a huge variety of applications in the railway sector. And I would like to only state a last sentence about the future. So we think that also swarm-based behavior of those sensors in a network can reduce infrastructure cost and jump over system borders, meaning that when I'm able to locally analyze, analyze data communicated in a swarm-based network, then I can decide to communicate this data to another swarm, which is only dynamically establishing network communications. And at the end, I transport only information to infrastructure or to other interested person or user of the data, and therefore I can jump over those system borders because interfaces are more and more further interfaces are not necessary to this swarm-based propagation of information. Thank you very much for your interest, and we are open for questions and would like to answer them. Thank you.
Yeah, thank you very much. Please continue. Yeah, thank you very much for your interesting presentation. I have one double echo here in it, but now it's better. Yeah, thank you, Paul. Thank you, Carsten, for this very interesting presentation. And I can only repeat the feedback that have been given for the chat. It was an interesting presentation, and in fact, we have some questions there. Therefore, I will share the slide with all the questions, and you can read it then and immediately start to answer them.
Okay, yeah, thank you. So the first question, what is the sampling frequency of the sensors? Example given accelerometers of the sensor platform. So due to the fact that we use digital accelerometer sensors, our sampling frequency is nearly 1 kilo sample per second in 3 axes. But of course, due to the fact that we have further interfaces, also analog interfaces, we can also go on other acceleration sensor with other principles, and this is possible at least to detect up to 16 kilo samples. So, for example, we have a microphone installed. It's sampled with 16 kilohertz. Okay, next question is some applications using UVB, UWB. Very good question. We think that this is an upcoming chance to be more robust in communication, and maybe also to overcome the problem of crowded bands. We do not have an application example yet, but we have started a research project to research and develop a UWB solution for the industrial context. So because there are some solutions already in the consumer market available, but they are closed shop, and it's not clear how standards are evolving, and therefore we started a research project to do research work on that. But very interesting question. So the next one is it possible to use the smart sensor to monitor rails in order to use this information to generate a digital twin for laboratory testing to evaluate wear, noise, corrosion? Also a very good question, but also very complex, I think. So I have to honestly say we are not the experts in digital twins, and also in generating the algorithms for maintenance and predictive maintenance. So what I can imagine is that in principle, smart sensors could be spread out along the track. It's absolutely imaginable that they build up a sensor network and measure, let's say, vibrations of the track and velocity of the trains and some other parameters also, like temperatures. And what I maybe forgot to mention is that we also have LiDAR sensors. We have some infrared-based thermal sensors, which can be maybe used for measuring temperature of components at the train. And all these data could be feeded into a model, or in something like a data model, at least for behavior analysis and to form a digital twin at least. But I think there's a lot of expertise needed from different parties, trains supplier, infrastructure supplier, and also measurement guys. And yes, good question, but also a very complex task.
Yeah, maybe I can interrupt you for a moment because when looking at the STARS project, there are so many expertises coming from the different technology centers there. And we have 5 technology centers in the STARS project, including the Fraunhofer Institutes in Berlin. And I remember a tutorial performed some months ago by the Links Foundation in Turin. and they talked about digital twins, and maybe there could be established a good collaboration with this. And for sure, in the STARS project, we gained so much context also to tech-savvy companies which have some expertise in different technologies, and I guess that could be a good added value to strengthen these network and this collaboration. Next question, please.
Yeah, thank you for this advice. Could you tell us where has been the Belize positioning solution implemented? It is considered as a substitute for current ERTMS positioning solution.
Okay, I think I can combine both questions because they're quite similar. No, it's not considered as a substitute. It was a research project with a Spanish partner, Autodrive Solutions, and they are sitting in Madrid, and it was their idea, their patent, but I'm not sure. I don't know if it's considered as for something. We are just made the sensor. What the following steps are, I don't know. Sorry.
Yeah, this could be an offer here. The next question: would you be interested in larger scale demonstrations in daily rate traffic? That was one question from one of the participants from Sweden, which have good connections with Tavik Furket, the Swedish infrastructure manager.
Yeah, we are completely open for collaboration, and we are always interested in let's say field testing and field experience if we gain that. For larger scale demonstration, of course, we have to do maybe some engineering before, but in principle, we are glad to get in touch with people who would like to test the technology, who would like to do a field test or some kind of a prototyping phase to see how the system is supporting the measurement task and it's performing.
Mm-hmm. So that was not the last question because I have, you got a thumb here for this answer, and Peter was that person. He asked this question and he put also his email address into the chat. You can easily find it. So it was not the last question. I have another one. What can you tell us about the future railway mobile communication system which replaces the GSMR?
I have to honestly say that I'm not the expert on that. I do not have some insights on this special topic. Sorry for this.
So I have another question here, and I have to copy it into the slide. Give me 1 second. Maybe you can read in parallel. And the question is, by Mr. Munoz, can the sensors fulfill electronic onboard components regulations?
Yes, I think this could be possible. Yes, so if I understand the question correctly, this means that we talk about some self-adjusting algorithms or some self calibration algorithms, or maybe also some self-configuration tasks. I think this is a very interesting topic in design, but also in implementing the operating software on the device. I think yes, indeed, this is the future to not only use the sensor data for the measurement itself, but also use the data for configure and calibrate the system itself. There are some tasks to do. It's not working out of the box, but it's a good topic to work on this.
Yeah, I tried to copy one additional question from the chat, but as soon as I wanted to do it was not even possible longer. Maybe the questioner could open his micro and raise the question directly. And here is an addition of the question, of the further question of the sensors fulfill electronic onboard components regulations. The question was more related with EMC compatibility, vibrations, and so on. Could you say something about this?
Yeah, I think EMC is I think EMC is more driven by the design, by the engineering phase. Before I could actually bring it into context with also vibrations, and maybe if the person could leave his contact, it would be. I would like to get in touch also with the person. Then can we discuss it maybe face to face or bilateral?
Yeah, that could be a good option, and I guess this person will be ready to leave the contact data. And there is an additional question: are your beliefs used on any railway lines in the world today?
Since these are not our balises, that's the concept of our partner, Autodrive Solutions. So he was talking about using it for commuter trains in Spain, but since we're just building the radar sensor, I don't know if he's actually using them. I know there was a plan to test them.
Yeah.
Maybe could we arrange the contact to the who are interested in this?
They are building several sensors for trains. I can write it just in the chat. Okay.
Yeah. You must know that we have much Spanish participants here because the guys from Spain are very active in register to our STARS tutorials, and we have also two cluster organizations being partners of the STARS project. And yeah, thank you also for that. There is another question, and we have time for questions. It is not even 12, and please be very, very busy in the chat for your questions. And yeah, according to the presentation, smart sensors can be mounted on places quite difficult to reach. Does this compromise maintainability? Do they need to be fixed as soon as one of them stops working, or would it be possible for a train to continue its normal operation under this circumstance? Very interesting question, I guess.
Yes, exactly. It's very interesting, and exactly points out the advantages of the distributed sensors within the network. So I think there are some sub questions in this question. So I think the idea is exactly to place these smart sensors at places difficult to reach. And they have to be built, of course, very robust, but it's maybe a workaround to put, if the functionality is absolutely needed, a second one nearby, because and this is the next question. It has not being to be fixed, because if we consider this kind of networking, we can place several sensors around the topic, to gain at least more data, to have a more complex view on the measurement task. And the advantage is if one of the sensors fails, the other one can take over. And if maintenance is scheduled for a dedicated time, then these sensors could be fixed then without the need for being or stopping of operation.
Yeah. Are there some further questions? You can even use the chat or open your micro or for hand raise, and then you can start with your question. Don't be shy to do so. We have still some minutes time. If no questions are for the moment, I will continue with some slides to tell you what is on the list next. I already mentioned that we have tutorials, still have some tutorials in connection with the STARS project. And for sure, if there are some other questions, you can you can think over and raise a question after that. So yeah, that is a slide already prepared for the further questions. And that is nearly the end of our STARS tutorial by today. And as I mentioned before, and the link is already in the chat, we have a STARS Project YouTube channel where all the STARS Project tutorials will be in it. Of today, for sure, even not because the recording has not been finished yet, but I already have online the tutorials from Monday on EU funding opportunities, and on the 6th of September, also performed by Fraunhofer, but more by the Neighbor Institute, focus on artificial intelligence. And yeah, the link to the YouTube channel is already in the chat. You have to scroll a bit to find it, but you will find it. And there will be 2 remaining tutorials on the technological innovation analysis, which have been performed by our project partner and technology center from France, Reliability, and it is the third of 4 tutorials here on assets for automated, autonomous, or remotely piloted operations and network management planning and control. We have there some presentations from Relenium itself, but also from Alstom, and a third presentation from the well-known Gustav Eiffel University, which is also specialized in railway research. And it will be tomorrow from 11 to 12:30. Registration is still possible. The link is already in the chat. You can follow the link coming to the website of the Cluster Transport, Mobility and Logistics in Berlin and Brandenburg, which is the landing page for registrations for all of the STARS tutorials. And we will have another tutorial when I will already in Gdansk for the Traco. It's 1 week later, same time slot from 11 to 12:30 on Thursday, 21st of September. It's the fourth and the last part of the technological innovation analysis did by Relenium in course of the STARS project. It's on regional rail services, innovative railway services to revitalize capillary lines and railway multimodal and intermodal transport. It is to be said that that Relenium identified during this technological innovation analysis 8 innovation trends which will have a major impact to the future development of the European railway system. And the task of the STARS project for sure was and is to tackle this issue, especially by small, medium-sized enterprises, with the use of advanced technologies to modernize use cases, to identify new use cases, to manage the process of digital transition and also on green transition. Yeah, the registration link for this tutorial is not even in the chat, but I will do it in a second. And yeah, further questions? I give you some seconds time, and I need some seconds time to copy this link, registration link for the last STARS tutorial. All right. It seems not to be the case that there are further questions. For sure, there will be a follow-up email with a link to the YouTube channel, as well as I hopefully you can agree, Paul and Carsten, with a PDF version of your presentation. And for the moment, if there are no questions, last chance, then thank you for your attendance, and have a good day. Maybe busy days, because September is very busy also to us. And it's also the last phase of the STARS project. We will have a final event on the 26th of September in Brussels. And maybe I provide you some information on this with the next occasion, maybe tomorrow for the next tutorial. So if you are interested to hear our tutorial tomorrow and you are not have been registered so far, please do so. If you are interested to find new contacts with potential interesting partners, please use the STARS Hack and Match Events meeting platform. And yeah, see you soon, and have a nice day. Bye bye.
Thank you. Bye bye.